that kind of does our quick little tour of file types and the compilation process. And now we're going to spend half the amount of time we just spent looking at tools that actually help improve this process. So let's just do a quick review. We were working with C, so we were using star.c files. Those are our source files. They're where we write the human readable code. For C++, it would be a .cpp file. Similarly, we have our header files, our star.h files and star.hpps. Those are the contracts we make with the routines we're calling, with the functions we're calling, right? They tell us how those functions are going to be used, so we don't have to, have all that information in one file. They're a little shorthand telling us, what the API is. We have object files. Object files are files using the computer language, the bit code. They're star.os on OS X and Linux. They're OBJs on Windows. And then we have our executables, the programs we can actually run. Generally in Linux, we're not going to use an extension, or on OS X. On Windows, it'll generally be an exe. We have to have a main. For us, the main was in high 1 and high 2. Okay, so those are just kind of the file types, kind of set this up. We have static libraries. Static libraries in general are .a's on Linux and OS X and star.lib with MS Tools. They're object file archives. They're essentially a bunch of .o's kind of thrown together. The linker looks for the symbols you actually need. And then we have this shared libraries thing, .so, .dylib, .so on our Linux systems, .dylib on OS X, and .dll on Windows. Now the cool thing on Windows, on OS X and Linux, is that the .so and .dylib contain everything you need. It contains both the contract you use when you link to set up the linkages and the actual shared library file that'll get loaded into memory when you run. On Windows, you will have an import library .lib that tells you the contract. You'll have to link with that, and the DLL is the separate shared library file that'll get loaded into memory when you run. Okay, so that's kind of an overview of this whole build process, and it's been a wild ride. It took us a little over an hour and 15 minutes, maybe something like that, maybe an hour. Yeah. So we have 2 more topics to cover, and you would think that we're going to be here till nighttime, but we're not, because it turns out that what we're going to focus on now is we're going to focus on the shortcomings of something like a build.shell. The build.shell file has a specific set of commands that get executed. They always get executed. There's no conception of, well, I already processed this file and the file hasn't changed, so I don't need to process it again. Or, this function, this program uses a function that the other programs didn't use, so now I have to go in and compile something new. So what we're going to do is we're going to be working on these things. We've kind of set up, we know we can control everything. We've shown you step by step how you can control each of the phases of compilation. And now we're going to kind of use makefiles to automate that so that we can actually encode dependencies among our programs and among our files, our subroutine files, our function files, so that we can kind of both get concurrency where it's available, right? So if 2 files don't depend on one another, we can compile them both at the same time if we have enough cores and enough processing power. We're going to get it so that we don't have to start over again. We don't have to run every command in build.shell. We just have to run the ones that haven't been run yet or that haven't completed successfully. So if we find errors in the 17th file of an 18-file series, we don't have to compile the first 16 again, right? We just start from where we left off. If we change a file, we can just change those things that depend upon it. And this, because of these reasons, this really doesn't scale. I left this rarely used in practice because in big systems, Commercially, you will never see this deployed, but I bet if you go into a lot of developers' personal directory spaces where they're just hacking around, I bet you'll find this a lot more often than you think. But from a building a system, building a complex program kind of aspect, it is rarely used in practice, and we'll see that it's becoming vanishingly with the advent of meta build systems like Cmake and others. I'm blanking on the other ones right now. You'll find out that they're becoming less and less necessary. So let's talk about Make. We talked about build dependencies a little bit, or at least I mentioned them. And what they are they're systems that define what pieces of code depend on other pieces of code. So for our High 1, High 2, our latest version of High 1 and High 2, this is kind of our build dependency chart. At the base, we have 4 C files, right? They're source files. We hand generated them. They weren't generated from some other, the output from some other program. So they really have no dependencies. They are what we wrote them to be. We don't have to worry about any other code in order to write the C files, or in order for the C files to exist. There's nothing else that needs to be done to create them. When we talk about auto-generated code, these may in fact have dependencies. As your system description as your system descriptions change, you may actually have dependencies if you're auto-generating these. But in general, for what we're talking about, we can consider these C files to be the base of our dependency tree. They don't depend on anything else. Immediately above them is the object file. And there's a one-to-one correspondence between the C file and the object file, right? In order to create the object file, we need the C file. And as the C file changes, the object file also has to change, right? So we have 4 object file dependencies, and that's just a straight line. Now's where it gets interesting. Yeah, kind of. We have this lib hello. This is our shared library. This function includes hello 1.0 and hello 2.0, so it depends on both of those. So anytime either one of these changes, which means either time one of these changes, lib hello has to change. We don't have anything similar for High 1 and High 2, but when we get to the actual executables, High 1 instead of High 1.0 and High 2 instead of High 2.0, well, they depend upon the library and they depend upon the corresponding object file for the main. Okay, so if hello 1 changes, hello 1.c changes, hello 1.0 has to be regenerated, lib hello has to be regenerated, and both High 1 and High 2 have to be regenerated. And that's kind of how you follow this, right? You follow from the thing that changed up through to see, how you get here. Or conversely, you can look at this, and at each branching point, you can see, whether anything along that branch has actually changed. And that means if something has changed, then this has to be regenerated. So if we look at our dependency graph, right, this kind of captures it. At the upper level, to build everything, we need High 1 and High 2. They are our upper level target. To build High 1, we have a dependency upon High 1.0 and our shared library. High 2, High 2.0, and our shared library. High 1 depends on High 1.c. High 2.0 depends on High 2.c. Here's the dependency for the library, and then the dependency for the .o files on hello 1 and hello 2. This format with a target and then a colon and then the things that it depends upon is pretty much the standard format for a Unix makefile or a Linux makefile. What it doesn't encode is how to get from, the dependencies to the target. And some of these, for example, these are pretty much, unless you have some fancy flags, these are pretty much known. You don't necessarily have to encode those. You don't have to give operations for those. They will generally work. I want you to use operations for these when we're talking about the test or when we're talking about the lab. I want to see that you have all of these dependencies kind of understood. All right, so let's look at what a make file might actually look like. I'm going to steal this. You'll notice that I added one more dependency. I added a dependency for clean. You almost always want a dependency for clean, just because it is a very useful thing. You want to be able to reset yourself to a known state. I'm going to have to clean this up just a little bit, but let's do that. The other thing to remember is that for a make file, this line can be right up against the border. The next line down has to be separated by a tab, not by... Okay, so I see what's going on. By a tab, not by a space, or not by spaces. If it doesn't, it won't work. Maybe we'll try that, but we're running out of time, so maybe not. And the cool thing is we can do something like make clean, and we'll get rid of all of our intermediate steps because I thought that was important. And now we can do a make, and when we do the make, what it's going to do for us is it's going to run all of our compile steps. And at the end, we hopefully end up with functions that actually work, high 1 and high 2. But the cool thing is, it's because we've encoded these as dependencies, we gain some other capabilities. In particular, what we gain is we gain the ability to come on. There we go. We have the ability to encode, well, since we know what the dependencies are, we only have to do stuff that makes sense. So if we do a make again, everything's been compiled, so we know that nothing has to be done, right? We don't do anything. We can do something like touch hello.c, hello2.c, right? And now when we do the make, we'll remake some stuff, but we'll only remake the stuff that actually depends upon hello2.c. So we'll remake hello2.0, we'll remake the shared library, and then we'll make both executables. If we do a make clean, we can get back to the start. We can do something like a make high 1, specifying just one of the targets, and it will compile everything required for that target. By the way, the default target is all the one at the top. The first argument is the default target, and you'll see that it depends upon both high 1 and high 2. So if we just do make or we do a make all, it will make both of them. Here we've just done high 1. If we do an ls, we'll see that there is no high 2 here, but we can come in and we can make high 2, and only the stuff specifically needed for high 2 will get made. Since we already have the shared library, the only thing we do is we make the high 2.0 and then link it together with the shared library. Okay, and both of those still run. Now, there's one dependency we haven't really covered. We have, if we look, we can do a grep on grep for hello.h, right? We had that that header file, and it's used in a bunch of different places. Hello.c is not being used in this compilation, but hello1 is, high 1.c is, and high 2.c are. So we know that we're not actually we don't have that encoded in our graph. We can even go through and do something like gcc-mm hello1.c. And that'll tell us that there is a dependency on hello.h. I think I have a -mt in there as well, but that's okay. Right, so we can look through here and we can see that this encodes the dependencies, and hello.h is actually a dependency of hello1 and of hi1 and hi2. We probably want to encode that. So in order to encode that, we have to actually go through and do something. We actually, if we right now, since we don't have that encoded, if we touch hello.h and remake, like we had actually changed hello.h, nothing's going to happen. So if we actually want to make this work, we have to go into our make file and actually add it. And maybe we want to add it to, I guess, here and here, and then here. Right, so we actually have to figure out where that's used, and then when we do, we'll remake the stuff that needs to be remade. All right, see what else we have to say here. And then this gets encoded, right? These red links show the dependencies we actually put in to our to take care of hello.h. Implicit dependencies, I already did this. I extended it for hi1, hi2, and hello1. Good. Okay. So that's actually kind of, where this works. And by the way, I talked about concurrency. So if we were to go in here and rerun and do make clean and do make-j4, that should do a concurrent build of up to four parallel executions. So for big functions, when you have a lot of processing power, that will help out quite a bit. Okay, so 10 minutes, a little over 10 minutes left. I think we can get through most of CMake as well. So this is the beauty about it, right? When you get a good make file pulled together, you get efficient concurrent builds, rebuilds. You only build the stuff you need. You don't build the stuff you don't need. You can use concurrency because you know what depends on what. So it's a good way of doing builds. As far as limitations go, well, you do have to maintain some stuff. You have to maintain the implicit dependencies, and that means that as people add .h files, you need to know about it. Particularly for .h files that correspond to an API that you're not actually looking at. Like for shared libraries or for libraries that you're using. It is platform specific, and things like GCC, etc. That's specific commands that need to be used on specific systems. If you change your commands, if you change the make file, unless you add the make file as an implicit dependency, things don't get rerun. And you saw that we put in a manual rule for cleaning up after ourselves. We could also put in a manual rule for installing. And it doesn't really work so well with Visual Studio and Xcode. But it is a good solution for a Unix file. So now let's go one step further. We now have an efficient way of doing things, right? We know why it's important to encode our dependencies. We've come up with a system on Unix or Linux that actually encodes those dependencies. And now what we want to do is we want to take one step further. We've decided that maintaining make files is a pain in the neck, and it is, especially for big systems. So we want to kind of look at where to go from here. And I guess I should have talked about these three first. We'll talk about where we go from here in just a second. Make files work on Linux systems, on Visual Studios. I said that make files don't work, at least, but they do work. You can convert back and forth, and I think there's actually even ways to make it work. But Visual Studios has its own system called, MS Build. It has an XML kind of file that describes all the same things that we kind of describe in our make file. Someplace in our make file. It does actually, you can create it and update it through Visual Studios. It does actually handle implicit dependencies. It does have built-in clean operations. It is fairly heavyweight and cumbersome if you've ever used it. At least it was. I haven't used it so much recently. It's, again, not portable. It's unique to the system. And you do need manual rules for install. And I think it's getting better at merging version-controlled branches, but I haven't really looked at that so much. And there are other build systems. Make is the canonical one. Ninja is an assembly language for build systems. So it's actually a build system like Make that's designed to be automatically generated. So it has a simpler syntax, a computer-driven syntax. MS Build, WAF, WAF, and SCons. They're also good build system-based frameworks. Okay, so now let's talk meta. Where we go from here. If we look, here's a nice overview. I'd take a look at this. 19 best open source systems for C and C++. And you'll see that at the top are Ninja, which is akin to Make, and then Cmake, which can generate Ninja. So the beauty of them is they're Windows, Linux, Mac. This says GNU Make is Unix as well. These are easily Unix as well, I believe. I haven't actually tried to run them on a Unix system. I'm almost positive Cmake runs on it, though. And then you get down into some of the other ones like Premake and Tup. But there are 19 systems here. Take a look at them. What I don't like about this is this interspersed meta systems that build systems with things like Make that generate executables from a Make file that can be generated by one of these auto-make systems. So it's kind of comparing apples and oranges on some things. But what I like is that two of them at the top actually work really well together. If you're on a Linux system, primarily, I've seen it work on other systems as well, like OS X. There is Auto Tools, which generates configuration scripts that it can generate GNU Make files. I've used that. That was kind of the predecessor, largely a Linux or Unix locked system that does the same thing that Cmake does in a more limited way and without a lot of the introspection support that Cmake actually gives to you. And then Premake and GYP, those are similar. They have similar capabilities to Cmake. I haven't actually looked at JIP. Premake was the one I was trying to think of earlier. But they actually allow you to build systems as well. We're going to concentrate on Cmake. If I don't get through this, I will take the start of Thursday's lab to kind of finish up. Maybe what I'll do is kind of rush through this so you're prepared for the lab, and then just go through a little bit slower on Thursday. But Kitware, local company up in Clifton Park. It's actually closer to me now than it is to me at RPI, but they built this around 2000 to support the Insight Toolkit. Prior to that, we had different build systems on Linux systems and Silicon Graphics and Windows, and they were all separate systems. They had to be maintained separately, and often one or more of them were broke because keeping things synchronous like that is actually relatively hard on complex systems. They came up with Cmake. I hated it for probably a year and a half, and then it just became obvious how much better it was as you start changing systems, as you do things on Windows and Linux and OS X and SGI's version of Unix, etc. KDE adopted it back in 2006, so they're one of the big Linux desktop manufacturers. We can look at them. Right, they're right here. They have a cool new Plasma thing that almost enticed me to spend $1,300 on a new system. I haven't yet, but it's tempting me every time I go there. And they still do use CMake, and you can see how to use CMake and how to get building with CMake on their system here. So that's kind of cool. And this was edited on November 10th, so that's kind of cool. It's still active. You know, you'll find a lot of projects that use it. If you have one project that uses CMake and you have another project that uses CMake, they tie very nicely together, so that actually helps. And we've got some documentation on the homepage for them. So let's write a CMake file for our code. So we have this make file, right? So we can look at our make file. And it looks like this, and it has a whole bunch of things, and we have, you know, some compile commands and some remove commands and some link commands. Okay, we're building our shared library. It's not horrible. It's a fairly simple system, so it's not all that bad. But we can come in here with a CMake lists.txt, and our make file will only work on Linux systems. Here's an equivalent CMake file for it. Basically, what we say is this just says what the minimum required version of CMake is, depending on the features you're using. This just defines we're doing a C project, and we're going to call it project hello. We're going to create a library. The library is going to be called hello, so that'll come out as libhello.so. It's going to be a shared library, and these are its dependencies, right? We don't have to worry about our compile line. We just tell CMake what we're going to do. And the beauty about not having to worry about the compile line is that this can work on systems with different requirements for compile lines. So you saw there were a couple of commands that are different on OS X. We know that they're all different in Visual Studios. Well, that doesn't matter. We specify we need a shared library, and we leave CMake to figure out what that actually means. Then we have one executable, hi1. It depends on hi1.c, and it's linked to our library hello. And similar, we have hi2. That depends specifically on hi2.c, but it's also linked to our library hello. That's pretty much all the CMake file is. And what we can do is the other nice thing about it is we can do what they call out-of-core builds. So we can create a new directory build, and all of the files associated with building and running CMake will be here. We'll just do a CMake ... That's the path to the CMake file. And what it will do for us is it will go out and introspect our system, figure out our C compiler, figure out all the other things that are necessary, what type of a system it is, and it will generate a make file for us. And if we type make, we can generate our make file, or we can use the generated make file to actually build the system. And our .hi1 works, and our .hi2 works, right? Really simple. On the other hand, the make file it generates is anything but simple. And this is because it works for a variety of different systems. It's defining where it wants things, libraries, directories, different commands that you may want to use. Throws together an installer, right? We can do a make install if we wanted. More importantly, we can do a make clean, which will clean up after itself, follow up with a make again. Okay. This is just checking dependencies. It checks all of the dependencies here and then tells us immediately that it found them. You notice that it didn't go through any of the intermediate steps. All right, so hopefully that was being shown. Yep. So it does, however, create a lot of different things inside that directory. Right, if we look, and if we dig down into the CMake files, there's a lot more stuff where it's pulling in things and just keeping track of everything it needs, including the configuration of CMake itself. Okay, where am I and how many? I think I have like 3 pages to go. I'm going to rush through these. You guys can leave if you need to. I'll go over a little bit of this on Thursday, but it doesn't make sense to stop where we are now. Actually, this is good. If I wanted to, I could go up one level and just delete the build directory, and all of the stuff that I created would be gone. It allows you to maintain clean source directories very easily. That's maybe the best thing of it. And then on top of that, it comes with this GUI. You can install it. So Cmake Gui, and that actually, hopefully that'll show up in the right directory. Okay, so that gives you this little GUI where you can kind of browse around and see, visually interact with it, see your source directory, see your browse directory. I always like to click into grouped and advanced, so it kind of allows you to see all of the environment variables if you want to modify them. I often run from the command line. I rarely run from this, but it is a nice way if you're looking to see what object dump file you're actually running, etc. It's a good way to see that. And then finally, let's go back to our presenting slides. And you can, by the way, specify whether you want it debug, release with debug info. So if you're trying to debug your system or you're trying to deploy it, you can pick those. It'll generate VS project files. I'm not going to take a look at those. It looks something like this, at least it did in previous versions of VS. I haven't brought it up this year yet. I don't know how badly that's changed, but basically you can build your libraries, your executables, etc. And we could even do things to help us debug. We can embed things like this, setting and looking at variables. We can embed them into the make file, to the CMake file. And when we do, we can give ourselves some idea of what's going on if we have to. Oops, did I? Yeah, so if we put them into the CMake file, I put them in when you guys weren't looking, right? That's just that. What we can actually do is we can use them to give us some information, right? So we can embed some information and then print it out, so we can see where we're getting in our make process or where we're getting in CMake. All right, that's the end. I didn't go too badly over 4 minutes. We'll try to go through a little bit of this. Probably the last few slides I'll probably go over on Thursday. I don't know that I'll tape it. Here's our summary. You can read that. You should understand it. And we'll see you on Friday for your lab on Make and CMake. All right.